We are ready to start our Q&A regarding your presentation to the conference. I need to ask my backstage if they have questions. Backstage gives me the note that the questions are coming momentarily. Okay. You have a nice office, Marc. Here is the question to Microchip. What are the limitations of the augmented driver? Topology, speed, voltage, etc. That's to Marc.
Okay, yeah, I can answer that. No problem. Thanks for the question and hello, everyone. So the limitations of the current offering which we have, which are the augmented driver as a module, they are mainly made for systems with higher power levels, so 20 kilowatt and upwards. Then it makes sense, but there is no open limit to the top and topology, so we can directly drive half bridges with that. And voltages, correct me, Tomas, currently we do offer 1200 volt and 1700 volt devices. And switching speed, I would ask Tomas to answer that.
Okay, Tomas.
So the question was about the switching speed, or?
Yeah, is it 50 kilohertz? Am I right? Can you confirm?
Yeah, it really depends on the load we are driving, but on our PCB-based gate drivers, we have a 3 watts per channel. So these 3 watts can be consumed for driver, light loads at high switching frequency or heavy loads at the lower switching frequency. So, but the real thing is up to 100 kilohertz for sure.
Okay, thanks.
Thank you, gentlemen. I'm looking to my backstage who turned the questions in. Here is the next question. Again, to Microchip. Why Microchip believe that among of actual known advanced gate driving techniques, augmented is the right one? That's something to Tomas and Marc.
Tomas, would you like?
Right. So among many others, let's say advanced gate driving techniques, there are a couple, right? Closed loop, open loop, current source and voltage source, and then one of them is active gate voltage control, which is in principle augmented switching is that it's very easy to programmable. So we believe that instead of active gate voltage control or to have something more advanced, the programmability and configurability of the gate driver, even on fly or offline programmable, is another way. Together with silicon carbide technology can be, spread in industry. So that's the reason, because the steps, sorry, it's very easy to programmable and it's very easy to change it. So that's the main reason we believe it's the right way.
Yeah, I'm not sure if I mentioned it correctly on my presentation. We do have a software, a GUI, so a graphical user interface, where you can make it very easy by entering parameters or graphically. Then you can implement all the steps. So very easy to do. So you don't have to resolder anything. So yeah, try to make it as easy as possible for our clients.
Okay, sounds good. We got the next question to Agnes. Thank you for the great presentation on X-FABs, SiC. Is there a plan for SiC CMOS allowing monolithic integrations? If yes, will there be an MPW runs?
Yes, thank you for the question. So as silicon carbide is a vertical device, you usually cannot do monolithic integration. So in the silicon carbide as itself, this will not be possible. And I don't know about any research that would integrate silicon carbide with CMOS, so meaning with silicon wafers. So there's an GaN on silicon, this is what can be done, but silicon carbide on silicon wafers, I'm not aware of that one. So sorry, not in the near future.
May I have an additional question? This is Tomas Krecek from Microchip.
Yes.
Yeah, so what about the monolithic integration of the, for example, current mirrors for current measurements and maybe one diode for junction temperature measurements? Is it feasible according to you?
I did not get the question. The measurement?
Yeah, so if we can monolithically integrate the silicon carbide MOSFET, for example, current mirrors, as an additional device can mirroring the drains or current for the measurements, current measurements. And second, if it's feasible to integrate, for example, PIN diode for temperature sensing of the, of the junction temperature, not only NTC using in the power modules. So that's because normally in I came from IGBT world. And silicon, of course, we normally use this technique for, for junction temperature or current measurements. So that's.
So, as far as I'm aware of, because of the nature of the silicon carbide device, so it's a vertical device. So you need always to contact the front to the back side, and that's not possible to integrate their other devices monolithically. You would need to isolate them completely, and you cannot connect them then in one wafer. So there might be some other ways to do this on an heterogeneous wafer level, but for the pure silicon carbide, I'm not aware that this is possible.
Okay.
Thank you. Thomas, I know what you are talking about. There are ignition IGBTs who have in the monolithic design a chain of diodes going around to open the device in forward conduction. That's the most used. So, but that's in silicon, and the limitations in silicon are also given. You have no really IC world combined with IGBTs.
Okay.
Or is my knowledge there out of range? You see,
I would say maybe if I can interject, there's probably two questions from Thomas. One is integration of ICs. The other one is maybe a SenseFET, right?
Yes, something like this.
So there have been published results of integration of SenseFETs and silicon carbide MOSFETs. Yes, it's definitely possible. Depends on the technology and use case.
David,
okay.
Thank you for the answer. But that's similar to silicon devices who had these features in the past to sense and good to understand that the SiC can have the same features like before in silicon.
Thank you.
Thank you, Thomas. Here we go. The next question to Microchip. Why Microchip use stepping of the gate voltage at turn on if there is no overvoltage phenomena?
Marc, probably for me question, right?
I leave the all deep technical ones for you.
Okay.
Go ahead.
Yeah, that's right. The last generation of let's say active gate voltage control, we have two steps at turn off. So there is obvious need to dump the overvoltage, right? And due to some stray inductances in the system, but turn on it's not really clear why we have the steps there. So I can just to explain here that you know, in principle in the turn on there is for sure a reverse recovery issue, mainly especially when the body diode is used. Body diode in the MOSFET is not really optimized for switching. It's not really optimized to be temperature independent device. So we see on the customer side a lot of issues with the EMI, EMC, quite significant losses during turn on. So, but mainly the oscillation and snappiness of the diodes bringing a lot of issues. So the steps, because the MOSFET is in principle, maybe someone will not agree with me, but it's a current voltage controlled current source, right? So, and by the step, introducing one step at turn on, we can control the slopes, the current slopes. And we know that the reverse recovery snappiness and reverse recovery peak is directly proportional to the slope of the current, which are being turned off. So that's the reason, and we can directly change the slope and like this dump the reverse recovery issues, snappiness, over voltage, over currents, and so on. So that's the main reason we have there one step at turn on.
Okay, Thomas. Let me summarize. It's a DVDT limitation tool to make the step.
Yeah. At turn off, this is a problem because we want to control voltage through current source, which is, MOSFET is in principle current source, voltage driven current source. And we want to control the DVDT by the current source through the stray inductances. So it's more difficult. So that's the reason we need there a little bit more steps, a little bit more resolution, because it's more difficult to control. But the turn on is we want to control DIDT, so the current, the slope, the current. Mm-hmm. So that's the and like this we can really change the snappiness of the diode and the behavior of the reverse recovery phenomena mainly in the body diode.
Thank you, Thomas. I think the backstage has a new question on hand. Oh, that's a question, a long one. It's addressed to Agnes. Application manufacturers want the performance of SiC, but this is on some tenths of micrometer on top of the wafer. However, we receive some 250 μ to 500 μ. It is needed as a carrier in the wafer fab. Does X-FAB see a possibility to keep the carrier part of the wafer at the fab for reuse, or replace it by cheaper material, carbon, in order to reduce cost?
Yes, thank you. That's indeed a very interesting question, and one that is also related to the question, how will the silicon carbide device cost develop in the future? So indeed, at the moment, we need a specific thickness of the wafer. First of all, it's hard to cut it thinner because you need the structure of it, and then you do the epitaxy on it, and then you backgrind. So you throw away roughly half away of the silicon carbide, and therefore also of the cost of the wafer. Currently, it is possible to backgrind roughly to 110 micrometer. There are some R&D development to go thinner, but that's actually kind of the limit because the wafer is really thin and it's starting to really roll and be like a paper on the end. But yes, indeed, there are some R&D developments that are going into the direction of splitting the wafer. There are several splitting technologies, and other companies are also working on that and using that, where really after the device manufacturing, instead of back grinding the material, you split the wafer roughly below the device, basically. And you can do this with acoustic waves, you can do this with lasering, we can use this with the cold split technology. So there are several approaches on that one. And indeed, you would then reuse the wafer, the base material, to again, after some polishing, reuse this in the fab. So there are some developments on that. At the moment, the hindering part is cost, because it's still quite expensive to do that. So the balance is not there yet to actually use that. But I expect that those technologies will become much more competitive and therefore cheaper in the future. So this will be definitely a part. And to replace silicon carbide is tricky, because you want the material properties of silicon carbide. So that's why I do not see topics like having an epitaxy on a different material. I think you would not get the benefits of that one. So I think when you want to have a silicon carbide device, you will have silicon carbide wafers with silicon carbide epitaxy on that.
Thank you, Agnes. A lot of future challenges that will be able. Semiconductor development is always something which goes in slow steps and must be proven reliable. Otherwise, it does not make sense. Mostly the first tests before they get over into volume production need time, sometimes years. Okay, the next question could be come up. It's again to Microchip.
Yeah, that is, I think, a simple one. Would you like to read it, or shall I directly?
For all the auditorium, if they have not the screen ready to read it, I will read it out. Does Microchip provide IC version of that technology, or only PCB-based gate driver versions? Okay, yeah. Go ahead.
Yeah, it's a good question. We get that question very often for the lower power levels, especially, that customers ask, hey, the board is too much for my application. So the request is there, but until now we don't have an IC version. So we are offering the board, the module version, and because we address the higher power applications first. But no one knows what the future will bring. So it's a request. We hear that very often.
It's the customer in general who will make the development in the product if he has the volume to buy it. That's what I have learned when I spent 12 years for application marketing for RCA, GE Solid State, and Harris at the end. So that was a challenging time in the 90s. That was the time getting IGBTs in front for applications. Now it's the wide bandgap devices. It's the same challenge to get them up front to the design engineers. Okay, I'm looking to my backstage. Still Microchip. Regarding the low inductance module, first, is that already available, and what kind of topologies do you support? does it also support the mentioned avalanche capability?
Yeah, that's an easy one. I can take that, Tomas. So it's always good if I also can answer something. So the first question was, I think, about if it is available. Yeah, sure, it's available for a long time already. So before we acquired Microsemi, I think it was available, and we are still developing new versions of that, not new voltage level, power levels, and so on and so on. So it's available. It's nothing of the future. It's there. It's a phase lag inside, and we are using. So the second question was the avalanche capability. So you know that Microchip has a very, very high avalanche capability of the silicon carbide devices, and as we are now using already for several years our own devices, yeah, it's also valid for that. And that maybe the question came from the idea: does it also help with the ringing? I'm pretty sure, Tomas, you can correct me, but it also helps a little bit with the ringing, that it doesn't hurt our devices so much than if they don't have this avalanche capability. Yeah.
Okay, Marc, as you just mentioned, since you acquired Microsemi, I still have in memory that Microsemi once acquired APT in Oregon. So that was the power side more at Microsemi.
Yeah,
so
you are right.
there is a long way of getting companies together.
Yeah. So, but thanks that you mentioned that, Bodo, because it's interesting. So maybe Microchip, the name Microchip is not always linked to power, but we have more than 20 or 30 years experience with that. I think the first silicon carbide devices were sold to the market in 2003 or so roughly 20 years ago. What I have heard from the colleagues, and you said the APT, so they were acquired in 2006 from Microsemi, and Microsemi was a company with many different departments, many different companies, and we acquired them, we integrated them smooth, and now it's part of the overall Microchip environment and value and so on. So yeah, we do have the long year experience with that, like you have. So we know each other a long time already, yeah. So from Paris.
And
yeah.
And yeah, at a certain time, I recognize how old I am, and I spent roughly more than 50 years in the industry from the very beginning. So let's see the next question. That's to WeEn. Can you introduce the benefits of the devices you're going to launch next year in regards to efficiency? That's to Jan.
Yeah, I can. Okay, so our company has both industrial and well, we have industrial MOSFETs and diodes and silicon carbide. In the beginning of next year, we are starting to introduce a whole range of 650 volt and 1200 volt silicon carbide diodes. And the silicon carbide diodes have a choice for standard VF or low VF. And so in terms of efficiency, let's look at the diodes first. So for diodes, there is always switching losses and conduction losses. And if the switching speed is not too high, you may want to opt for low VF diodes. We call it generation 6, and it's industry standard designation. Generation 6 low VF diode have a lower VF instead of 1.5, about 1.25 volts. And that means you can make lower conduction losses, and that's a point in efficiency. But it's horses for courses. If you do a very high switching speed, you may want to opt for our Gen 5 device who have a higher VF, and that could be better in efficiency than the Gen 6. So it depends. For MOSFET, very important is that our devices have very good RDS(on). We have a low specific R(on), so that's resistance for a square centimeter of silicon carbide material. And for our planar device, our first MOSFET that we introduced last year is a planar device. We are working to introduce in the future trench devices with even lower R(on), but also our planar device we will introduce in the course of next year, much lower RDS(ons) for the MOSFET, down to 20 milliohms for 1200 volts.
Thank you, John. More questions from the backstage here are coming. Again to Microchip, how important role play proper positive and negative gate voltage basing on overall SiC device performance?
Hey, Bodo, probably question for me. This is Tomas,
yeah,
Microchip.
Go ahead.
Yeah, so this is a, let's say, never-ending topic. Probably this arose or was induced by the many different technologies currently available, and each customer, each manufacturer recommending different voltage. So I believe, yeah, positive. It's very important regarding the RDS(on) and so on, how to get maximum from the device. Negative, of course, we know. At least for Microchip dies, we need negative to be fully off the device. So we strictly recommend negative biasing to avoid any cross-talking between switching node and gate pad. And because we are speaking right now mainly about our gate drivers and advanced gate driving, so that's the reason we are providing the programmability. So the customer with our PCB-based gate drivers can program a positive part and the negative, either negative from 0 to -6 and positive, I think, from 15 or 14 to 20, 21. So yeah, so this silicon carbide technology today is from performance point of view, it's really requiring the recommended gate voltage in the positive way, and for, let's say, safety operation, there should be to have enough negative biasing, at least for us. So yeah, it's very important, and any designer should take into account what positive and negative biasing is the right one for the current technology, and we are providing you the programmability and configurability there.
Okay, Tomas. I'm aware that this was for silicon devices in the past, for high power IGBT modules or discrete devices, and very often also the case. Okay, well, for the next ready, that's a question to Alpha and Omega. Can you share the 650 volt, 750 volt SiC MOSFET release and roadmap plans? David.
Yeah, sure. So I'm sure if you go to the website now, it's all 1200 volt devices. The 600, so in the next month will be officially be on the webpage, orderable. For the 650 volt, those are intended for the automotive, for the industrial market, and the 750 volt MOSFETs are the automotive qualified MOSFETs. So two different versions you can choose from, and they'll range from 15 milliohms to above 60 milliohms. on the initial release, and then in the TO247 3 lead, TO247 4 lead, and more packages again next year. So again, 2 different versions, 650 and 750 for the different markets.
David, thank you for your answer to the subject. I got the sign from the backstage that we have no more questions coming in at the moment. And I think we have had half an hour of fruitful discussions. I will say thank you to all of you, and I wish you a great rest of the day and also peace, which is important on our planet.
Thank you very much.
See you at one of the upcoming conferences and shows, and for sure we are planning next year again a real conference.